So this question asks us to show that any tree is two-colorable. So a high-level intuition for this is that we can always destructure a tree into levels, like we've done right here. And we can color even levels with one color and odd levels with another, and it works out nicely. In order to formally show how that this works, we will give a proof by induction on the number of vertices. So in a proof by induction, the base case is just phi is equal to 1, which quite naturally works because you can always two-color a single vertex. Then we do our inductive hypothesis. Any tree with less than or equal to k verts is two-colorable. Yeah. And then we do our inductive step, which looks a little bit different because we're doing graph induction, which, as we saw in the previous question, works a little differently. And we say, suppose we have a tree on k plus 1 vertices, some so we remove some arbitrary vertex w. And the unpleasant thing here is that, for instance, in this case, if we just remove the top level, the root node, what we're left with is not a tree, but a disconnected graph with two separate components. But what we can say is that each connected component, however many connected components we're left with, we know that each connected component has to be acyclic because it was part of a tree initially, and so it can't contain any cycles. And since each connected component is connected by definition, we have that each connected component must be a tree, and crucially, it must be a tree of size smaller than k. And so, as a result of that, we can apply our inductive hypothesis to the however many connected components we're left with. And so we know that for these smaller subtrees, a two-coloring exists. So for example, I've drawn one out here, where you have blue and red and blue and red. So we've successfully managed to two-color each of the smaller subtrees. And what we know now is, after this, you can... the trick now is that essentially you can add back your vertex w, and it's connected to, at most, k other vertices. So this is the extremely basic case where you have one root node with k children. And so, essentially the argument is that we can color w with one of the colors that we have used so far. So in this case, we can just color it orange, and it all works out nicely. However, there's a case where, for example, we could have chosen to color this tree with the reverse. So we would have two blue nodes, and an orange node in the top. So initially, this seems like it breaks our theory, but then we realize that, oh wait, we can just cycle nodes within a connected component. So for example, if we wanted to, we could swap blue and orange here, or blue and orange here. Let's just do the second one. So we have two orange and one blue. And then we can wire them back up to the original orange, and everything works out nicely. So the core is that once we have a k-vertex graph, each component is a tree. Therefore, it's two-colorable. And as we saw from the imagery earlier, plugging W back in is still two-colorable. Yeah.